Well, we solved some one-step absolute value inequalities. And now we're going to look at solving a multi-step absolute value inequality. And since we're dealing with an absolute value inequality, we are going to set up two cases. And so let's go ahead and set up our two cases and then solve them both. So now in my first case, I'm going to set up just pretty much like I see it. Except I'm going to remove the absolute value symbols. So I got 4x minus 7 is greater than 13. And this greater right there tells me that I'm going to end up with an OR statement, which is going to be the union of the two solution sets. Now in my second case, I'm still going to have the 4x minus 7, and I'm going to set up the negative 13, but I've also got to flip that inequality symbol. Kind of flip that inequality symbol to a less than. So my second case then is 4x minus 7 is less than negative 13. Well, let's go solve our first case. So first we're going to add 7 to both sides. So the 4x is now greater than 20. 13 plus 7, 20. And we're going to divide both sides by 4 so that x is greater than 20 divided by 4 is 5. So x is greater than 5. And then we got our second case. And again, I'm going to add 7 to both sides. So we got 4x is less than. Remember, we had to flip that inequality symbol from a greater to the greater than to a less than. And let's see, negative 13 plus 7 is negative 6. We're going to divide both sides by 4. So that x is less than negative 6 over 4. And we can reduce that where x is less than negative 3 halves. Now, let's try to put this on a number line. So I'm going to draw a number line. And let's stick 5 out here. And we can put 0 in here. And then right about here, let's put a spot for negative 3 halves. Okay, so in our first case, we said that x is greater than 5, and since it's greater than and not greater than or equal to, we got an open dot at 5, and our solution set extends out here to the right like this, out to positive infinity. And now we got x is less than negative 3 halves, and again, I got an open dot here at negative 3 halves, and my solution set is going to extend out here to the left, out to negative infinity, and there we have solved it and graphed it on a number line. Let's look at our second example. Here we got the absolute value of 5z plus 2 is less than and equal to less than. That means it's an and statement. I look at my original statement to determine whether it's or and. Greater is or, less than and equal to is an and statement. So it's going to be the intersection of the two solution sets. It's whatever is going to make both statements true, both cases true. And let's set up our two cases. Let's put this maybe in a different color. So now we got 5z plus 2 is less than or equal to 17. And our second statement is, second case is 5z plus 2, and we'll flip the inequality to greater than or equal to negative 17. And now we're going to solve. I didn't get the plus 2, did I? Plus 2 is greater than or equal to negative 17. That's my second case. Flip the inequality and change the sign of the constant. All right, well, let's see. Let's subtract 2 from both sides on this first case here on the left. And that's going to then result in 5z is less than or equal to 17 minus 2 is 15. Okie dokie. And we're going to divide both sides by 5 so that z is less than or equal to 3. That's one of our solutions. Okay, now let's do the one on the right. So we got 5z plus 2 is greater than or equal to negative 17. We're going to subtract 2 from both sides, and this is going to result in 5z is greater than or equal to negative 19. And we're going to divide both sides by 5 to isolate the variable, and 5 is z is greater than or equal to negative 19 over 5. Let's see, which would be 3 and 4/5, negative 3 and 4/5, or I might just put it in a decimal. Z is greater than or equal to negative 3.8, which is the same as 3 and 4/5, negative 3 and 4/5. Now, let's graph this on the number line. So here's my number line. We're going to put 3 right here. Let's say that's 3. And over here, as well, we'll just put a 0 in here for reference. And let's say over here we got 3.8. Let me change that to a slash mark rather than a dot. Okay. All right, so now remember, we're talking about the union of the two solution sets. So if z is less than or equal to 3, I got a closed dot here at 3, and that solution set is going to extend out this way, all the way to negative infinity. And then we've got z is greater than or equal to negative, and that's negative 3.8. Put a closed dot there, and that solution set is going to extend out this way to positive infinity. But my solution set is the union. So it is between this negative 3.8 and positive 3, and that would represent the union of my, not my union, my intersection, the intersection of my two solution sets. So, if we start off with a greater than or greater than or equal to, we got an or statement. It's going to be the union of the two solution sets. If we start out with a less than or less than and equal to, it's going to be an and statement, or the intersection of the two solution sets. I set up the two cases just like I would for any absolute value expression, or equality or inequality. Remember, in my second case, not only do I change the constant that is outside the absolute value symbol from a positive to a negative, but I also have to flip the inequality symbol. 2 steps right there to remember. Just persevere. Persevere. Don't give up. You can do it.